So we discussed chapter 15 about acids base. So chapter 16 is we go on acid-base equilibria. So what's the difference between the two? So we could say chapter 15 is based on the definition of acids and bases and how to get pH higher, or we could say strong, the pH of strong acids and strong bases. Now, if we have weak acids and weak bases, what usually happen is they undergo equilibria. So we could say chapter 15, chapter 14 is a combination of this chapter 16. So if we have a weak acid, okay, so the simplest acid-base equilibria are those in which weak acid or a weak base reacts with water. So if we're going to look at the general reaction between a weak acid, which we put as a generic HA, reacting with water is going to produce H3O plus and A minus. Okay. Now, as you're going to look at this, unlike the strong acids that has a one direction arrow, if you have a weak acid, you have a double-sided arrow, which means that the system is in equilibrium. Because the main reason for that is not all weak acid dissociate 100%. Or we could say weak acid, the reason why we call them weak acid is because they don't undergo 100% dissociations. Most of these weak acid, they just dissociate to a certain extent. So we have here a system in equilibrium. So if we have a specific weak acid, okay, that we can use here, we could say the acid that we can find in vinegar. So when it reacts with water, it produces a hydronium ion and acetate. So we could say this is the generic one, HA. So when you have here, you have H3O plus and A minus. And if you're going to look at the law of mass action here, so if the law of mass action that we have, we're going to write it like this. Now, as you could see, this one is a constant, so you can incorporate it with your K, giving you a K that is known as Ka. Okay, so if we're going to just write the Ka for the dissociation of a weak acid, we may end up with this one, with this general equation. So this is what we call the acid ionization or acid dissociation constant. So we don't include liquid water in the equilibrium constant expression, okay, because water is a constant when it is a liquid. We only what we could include those that are aqueous in nature. Okay. Now, if we're going to look at this acid dissociation constant, one way to know if your acid is weak, if you don't know or not able to memorize the 7 strong acids given to you, once you're given the Ka, automatically it is a weak acid. Now, what does the Ka tells us? What information that the Ka convey to us? So usually Ka tells us the strength of a weak acid. And the way that we're going to look at it is the higher the Ka value, okay, the stronger is the weak acid. So even though they're weak, they still have different strength. And the measure of their strength has something to do with the Ka value. So if you have the Ka value, and you are asked to determine which is the strongest weak acids, all you need to do is find the highest Ka value. So as you could see here, you have acetic acid and benzoic acid. So between the two, benzoic acid is a stronger weak acid compared to acetic acid. Okay, there's also a table that I have here. So in the phosphoric acid, so phosphoric acid is a weak acid. Okay, and it has three dissociable hydrogen. So as you could see, the first hydrogen is stronger than the second dissociable hydrogen, which is stronger than the third dissociable hydrogen. Okay, so if we have a problem like this one, HF, HN2, acetic acid, and HCN, so all we need to do is find, okay, which one has the what we call highest Ka. So highest Ka will give you what? Lowest pH. Or we could say lowest Ka will give you highest pH. So you can only answer this question if you have the value. So if we're going to look at this, so these are the corresponding Ka of these different things. So as you could see, this one has the lowest Ka, and that thing is HCN. So we could say, okay, that's the one that has the highest pH. And this is the one that has the lowest pH. So if we're going to look at it, HF has the lowest pH or the strongest weak acid among these choices, and HCN is the weakest weak acid among the given choices. Okay. Now, when we deals with what we call Ka, we do calculations, and usually, okay, the calculations that we have, you're given the value of Ka and the initial concentration of Ha, wherein you can calculate the equilibrium concentrations of all species. And given the value of the Ka and the initial concentration of Ha, you can calculate the degree of ionization and the percent ionization. Or you can be given the pH of the final solution and the initial concentration of Ha, and you can find the value of Ka and the percent ionization. So if we're going to look what we have discussed so far, you can be given pH, percent of degree ionization, initial concentration, and Ka. And then from the pH, you can find H3O plus. Okay, the relationship that they have is H3O plus is just equals to 10 raised to the negative pH. And then the percent or degree ionization, you can find the Ka. And using what is given, we can find the other quantities. So let's try to apply this what we call things that we have just discussed in a real problem. Okay, so if we have here a phenol, it has an initial concentration of 0.1 molar solution and has a pH of 5.43 at 25 degrees Celsius. So you are asked what is the acid dissociation constant of phenol, okay, and what is the degree of ionization. So how are you going to solve this problem? So just like what you did in chapter 14 on equilibrium, you can write the general formula and then how it dissociated, giving you A minus. So we have the rise thing. So initially you have what? 0.1 molar. You don't have any of this. And then you have what? Minus X, and then you have plus X here, plus X. So at equilibrium, we have 0.1 minus X, and you have here X and X. But what's the difference here? X is already given. So what is X? So usually your X is your hydronium concentration that you have. Okay, and that is also your phenolate. And you're given 5.43 there. So that means you can get the H3O plus concentration on that by 10 raised to the negative pH, and 10 raised to 5.43. That will give you negative 5.43. 3.71 times 10 to the negative 6. So that's the value of your X. So that's the one that you're going to use here. 0.1 minus 3.7 times 10 to the negative 6. So if we're going to look at the Ka will be equals to H3O plus times A minus over HA. And you're going to look at the value there, so that's 3.71 times 10 to the negative 6 times 10 to the negative 6 over 0.1 minus 3.71 times 10 to the negative 6, and this will give you around what? 1.4 times 10 to the negative 10. And for the degree of ionization, this is just equals to whatever's the value of your X over the initial concentration. So that will be 3.71 times 10 to the negative 6 divided by 0.1, which will give you 3.7, okay, times 10 to the I think we could just have 3.7 there, not 3.71. To the negative 5. And if you're going to want the percent ionization, all you need to do is multiply this by 100. So you will have 3.7 times 10 to the negative 3%. So that's how you solve the problem. Now, unlike the equilibrium constant, you can simplify this thing. Okay? In the area that we have here, the 0.1 minus 3.7 times 10 to the negative 6, you could just say that's equals to 3.1. You can make the assumption that the value of the X there is so small that the initial concentration is not going to be affected. Okay, or there's another assumption that we can make here, wherein we can simplify the assumption for acids base ionization. So what you look at here, the equilibrium concentration of the acid is most often the initial concentration minus X. If X is much less than the initial concentration, we can assume that subtracting X makes no difference. Now, you can have a valid assumption when the ratio of the initial concentration to Ka is more than, what's 10 to the 3, 1,000? Okay, it's more than 1,000. If it's not valid, you must use the quadratic solution to solve the problem. So I think that's the one that was not recorded during our last meeting. That's why I have to record it for the sake that you will have, let's say, a discussion on this one. So how is everyone? So we just finished chapter, what we call 14 quiz, right? And I just posted chapter 15 quiz. And today you're going to have what? Your OWL. So the exam will be on, yeah, 18, I think. That's when the exam is. So we might be able to finish the coverage for the exam next week, next meeting at the earliest. I'm not sure if I can finish this today.
I have a question.
Yep.
What was your plan with the homework after the exam?
Homework.
Is it going to be due the week after, like it's just a normal week instead of?
I think we just have to do the normal week now.
Yeah.
Yeah.
Okay. I think I might like that a little bit better.
I mean, it's up to you. I mean, I will. I already opened everything. Okay.
Oh, cool.
Yep,
Yeah.
because last time unknowingly I didn't know that I also didn't open the stop. So those who want to do it, you're going to do it. Those who want to take a break, you can take a break because after we could say we just have 1 month left after 18 in the semester. Okay, so I think it would just be the normal route that that you're going to have there. And I also posted, I don't know if you know it, I also posted the answer key for chapter 14 and chapter 15 reviewers. So if you have the classes, I'll try to see if I can show you the classes that I have. So if you have these classes that you have here, so you get the content. So see that one? So this is under the reviewers. So if you have a reviewers there, you have reviewers by chapters, okay? And then you have their chapter reviewers answer key. So I posted there some of the answer, how the answer, because I know all of you were going to go to my office hours and you're going to ask the same question at different time. So to minimize that thing, already giving you the answer key for chapter 14 and chapter 15. And maybe by the end of the week, chapter 16 will also be up. So I'm not sure if you can understand my the penmanship that I have there. Okay, it's the same thing as what we call that I did in the other reviewers, the exam reviewers that I have. So you could see that I have some reviewers here. So this one, exam 1 reviewer, exam 2 reviewer, exam 3 reviewer. So I think I have done my part to prepare you. So it's up to you if you're going to bite that thing. Okay? Because I'm still what we call a believer of the what we call when you write it, you will learn it. Okay? Even though we are in virtual learning setup, I still believe that if you write it, you're going to what we call learn about it. And I'm going to show you a video later on about it. Okay? That I still believe in the traditional way of learning. So the next problem that we have here, so the chapter, after you're done with the chapter, the main thing that you need to know here is you know how to get the pH of weak acid, weak base, and salt. Okay, aside from determining if it's a weak acid or if it's a stronger acid, if you're given different choices of weak acids and weak bases using the Ka. Okay, so the next thing that we're going to do, another problem here. So you have para-hydroxybenzoic acid. This is used to make certain dyes. So what are the concentrations of this acid of hydronium ion and of para-hydrobenzoate ion in a 0.2 molar aqueous solution at 25 degrees Celsius? So what is the pH of the solution and the degree of the ionization of the acid? So if you're going to answer this question, I think it's easy for you if you already have this what we call ice table or the rice table. So I'll try to do it in the whiteboard here. So you could put their HA producing H plus or H3O plus reacting with water and A minus. So that's the reaction. So initially, based on the problem, you have what? 0.2 molar para-hydroxybenzoic acid and you don't have anything. Okay? So what are the changes? Anyone? So this is a minus X and this is a plus X plus X. And if you look at the equilibrium, this will give you 0.2 minus X and this is X and this is X. And if you're going to write the dissociation constant for it, it's Ka equals to H3O plus times A minus divided by HA. Okay? So if you're going to look at the given, so if we're going to look at the questions that we have there, you're given 0.2 and you're given the Ka as 2.6. So you're asked for the pH. So what do you need to calculate? The one that's being asked is the pH. What do you need to calculate? Because you're given the Ka here. So what do you have? So you have what? 2.6 times 10 to the negative 5. And you have here x times x over 0.2 minus x. So we can make an assumption, okay? Let's say that this is just 0.2. So we can have the assumption based on the slide. So you have what? 0.2, the initial concentration divided by 2.6 times 10 to the negative 5. That is the Ka. So if it's more than 1,000, then we could say this one is just equals to 0.2. So what do you get? I think this is more than 1,000, right? 0.2 divided by 2.6 exponent negative 5. So that is around 7,000. What does this mean? So let's say if you're a billionaire, like Donald Trump, if you lose $1, you're still a billionaire, right? Because the amount that you lost is so small. So the initial concentration is still the same. But the question is, what do you need to solve to get the pH? Anyone?
The X.
The X. Because X there is equals to your H3O plus. So you have to analyze the problem. Oh, I'm looking for the pH. How do I get the pH? So if I get the H3O plus concentration, I can determine the pH. So the first thing that I'm going to do is I need to get X. So if we're going to do the calculation here, so this will become now what? 2.6 times 10 to the negative 5. You multiply it with 0.2, right? And you have here X squared. Okay, so you get the sum of that. What is that equals to? 2.6 times 0.2. So that's 5.2 times 10 to the what? Anyone?
I got a 5.2 times 10 to the negative 6.
I just need to answer this call. Sorry for that. There's some instrument that they need to use, and I'm the one who last used it. Asked me if I broke it. I said I didn't broke it. I used it fine last night. Okay. So you have 5.2 times 10 to the what?
Negative 6.
Is it negative 6? Okay. So this is x squared. So this is what? To remove the x squared there, you get the square root of both sides, and you get x equals to what? You get x
2.3
equals
times
to
10 negative third.
anyone? What do you get?
2.3 times 10 to the negative third.
Okay, 2.3 times 10 to the negative 3. So that's going to be your H3O plus and A minus. So once you get that, all you need to do to get the pH is negative log of 2.3 times 10 to the negative 3. And that will give you what? What do you get?
2.638.
Okay, so you have 2.64. Because the one that is given, the Ka that is given is what we call 2.6 times 10 to the negative 5. So you need two significant figures after the decimal. Everybody got that? Question. Analyze. Question? So the answer that you have here is just 2.64. So remember, in the exam, it's all multiple choice. Now, polyprotic acid. So let's discuss about this polyprotic acid. So when you have a polyprotic acid, it has more than one hydrogen or acidic proton. For example, your sulfuric acid, your sulfurous acid, your carbonic acid, and phosphoric acid. So you're going to deal with the polyprotic acid next week in your laboratory. So usually if you have a polyprotic acids and they are weak acids, they have more than 1 Ka. Okay, sulfuric acid, it doesn't have a Ka for the first hydrogen, but the second hydrogen has what we call a Ka, because the first hydrogen is what? Is a strong acid. Okay, so you don't have what we call the Ka for it. So remember, the Ka is only present in what we call weak acids. Okay, now how do we do calculations if we have a polyprotic acid? So this is just similar to how you do calculations in a weak acid. So you have your tartaric acid that is used in food products. So it has a pH of 0.1 molar. So you are asked, what's the concentration of tartarate in the same solution given the 2 Ka? So if you're going to look at the tartarate there, that is what? That is already the second acid, because if you're going to look at tartaric acid, you have it like this. And then when it dissociate, it gives you what? HC4O4O6 minus plus H plus. And then that's the first Ka. And then further dissociation will give you the second hydrogen and the tartarate. Now, what you're being asked is, what's the concentration of this? Okay, given the Ka1 as 9.2 times 10 to the negative 4 and the Ka2 as 4.3 times 10 to the negative 4. So if you're going to look at this, you could say, oh, I have an H2A that dissociate to give me an H plus and HA minus. Okay, and my HA minus further dissociate to give me an A2 minus and an H plus. So you have to do it one by one. Okay, so the first thing that you're going to do is you're going to do this thing. So that's the first reaction. And then once you have that thing, you further what we call dissociate it. So if we're going to solve this, I'm just using the whiteboard here. So as I've told you, the first dissociation that you have H2A, okay, plus water will give you H3 plus, H3O plus, and HA minus. So if you're going to look at the initial, it's 0.1 molar. You don't have anything here. The changes, this is what? Minus X plus X plus X. And at equilibrium, this is 0.1 minus X. And you have X and X. Now, if you're going to look at the Ka, this one, this is a Ka1. And you have here the H3O plus times the HA minus over the H2A. And you're going to use here the Ka1, that's 9.2 times 10 to the negative 4. And what you have here is what? X over 0.1 minus X. Now, we cannot make an assumption here. Why? Because if you're going to do the calculation here, what you have there, 0.1 divided by 9.2 times 10 to the negative 4, what do you get? What do you get if you have 0.1 divided by 9.2 exponent negative 4? It's less than 1,000, right? So you cannot make an assumption that 0.1 minus X is equals to 0.1. So you have to do it the hard way. So you end up multiplying this with this side. So you end up with what? 9.2 times 10 to the negative 4 times 0.1 minus X equals to X squared. And then you distribute this one, you have 9.2 times 10 to the negative 5 minus 9.2 times 10 to the negative 4 square X. Okay. And then if you want this to 0, what will happen? I will move the X here. So I will have a negative here to make it a positive. Okay. I multiply everything with a negative. So this will become 9.2 times 10 like that. So you have X squared here. Okay. So I will end up with this one a minus and this one a plus. Did you get that? Because what you're going to do here next is use this one. So negative b plus or minus b squared minus 4ac divided by 2a. So I'm just going to give you the possible X value that you will get here. Okay, so you will either get 9.1 times 10 to the negative 3, and the other is 1.8 negative 1.8 times 10 to the negative 3. So which do you think is the correct one?
A positive.
Okay, so this is the one that makes sense. So you cancel out that one because you're not done yet. You only solve for X here, which is the concentration of your H3O plus and HA minus. Because what you're going to do next, okay, is you're going to use that X value to get the concentration of H2A, HA minus, and H3O plus. So usually you could say that this one has the same value, which is just 9.1 times 10 to the negative 3 because they're X. Now this one is 0.1 minus 9.1 times 10 to the negative 3, which will give you around what? 9.1 times 10 to the negative 4. Am I right? Maybe 0.1 minus 9.1 exponent negative 3. Maybe I'm wrong. No, this one is 2. Around 0.0909. My mistake. Okay. Now what do we do next? We have to do the second one. The one wherein we have an HA plus water to give you another H3O plus and A2 minus. But there's a difference now. What are the initial concentration? You now have some initial concentration. This one. So this is what? 0.0091, right? And you also have here 0.0091. Now, does that make sense? Where do I get those numbers? So that came from the previous dissociation. So what happened, the changes that you have, this is what? This is minus X, this is plus X, this is plus X. And you have your 0.0091 minus X, and then you have 0.0091 plus X, and you have X. Now the question, what does the problem ask us to solve? If we're going to go back to the questions that we have there in the problem, we are asked to solve tartarate. So what is the tartarate now? That is the X in the second dissociation. That's the one that we are asked to solve. So how are we going to solve this? So we're going to write, okay, the Ka2, and this time we're going to put the one that we have here, okay? So we could say Ka2 originally is what? H3O plus times A minus over H2A. Not H2A, HA minus. So all we need to do is put the value that we have there. So this is what? 0.0091 plus X times X. And this one is 0.0091 minus X. And we can put whatever the value that we have here. I think it's 4.3 times 10 to the negative 5. So what can we say about the plus X and minus X? Can we make an assumption on that? Can we make an assumption that the plus x and the minus x here will just be equals to 0.991? Okay, so if we're going to do that, we will have it like this. So x is 4.3 times 10 to the negative 5. And your x there, that is your tartrate. So I want to go back to the problem here. So we solved the concentration here, but we have not solved yet this one. So what is the pH of 0.1 molar solution of tartaric acid? Which X are we going to use to solve that problem? Anyone? So this is your C4H4O6 concentration. Now, where do we going to get the H3O plus to calculate for the pH? Anyone? Hello? Where do we get our H3O plus? Can it be the one here? Because if you're going to look at the H3O plus that you have here, the X, and the H3O plus that you have here are what? It's just 0.0091. So you could say that's the only H3O plus sources that you have. So maybe when you get the negative log of that number, you can get the pH, and that would be equals to what? Right? Did you get that? Analyze. Well, I prepared the video that I told you to do it the old-fashioned way. So I have to post the recording, and kindly remind me to resume the recording when we're done. Okay? So the next one that we're going to talk about is the base. So you have the Ka for the acids. Now for the base, okay, you also do the same thing. The weak base, they will not dissociate 100%. So when you have a base, like in this general equation, which is a B, when they add in water, you form an Hb plus, because the base is usually what? Proton acceptor. Okay? And the one that is being produced if you have a base is the hydroxide ion. So if you're going to have a general equation for this, you have a base reacting with water to give you a proton, a protonated base and hydroxide. And if you're going to look at the equilibrium constant for this one, like putting in to replace the B, a specific base like ammonia. So you will have here ammonia reacting with water to give you ammonium ion and hydroxide. And the way that you're going to do it, if it's just the law of mass action, it would be like this one. And as you could see here, in the law of mass action, we included the water, but this is a constant. So when you incorporate it there with the K, this now becomes your Kb. Now, you may ask the question, Professor, how do we know if it's a Ka or a Kb? Anyone wants to answer that question? How do you know if you have a Ka or a Kb? Anyone? Yeah. So how do you know if you have an acid there or a base? Yeah, obviously the A from the Ka in the Ka came from acid and the B in the Kb came from base. But how do you know you have a Ka or a Kb? The answer there, for Kb, you have hydroxide as your one of the product. For Ka, you have an H3O plus or H plus. Because it's going to be useful later on when we mix your Ka and the Kb. Okay? So the same thing with the Ka, the Kb will tell us the strength of the base. The higher the Kb, okay, the stronger is the weak base. So if you're going to look at this, the strongest base here would be what? It's a choice between this one and this one and this one. But the winner is dimethylamine. And the way that you write the Kb reaction, as you look at it, is the water is the source of your hydrogen. So when you remove the hydrogen from the water, you produce a hydroxide. So one thing that you will know that you have a basic solution because there's a production of your what we call hydroxide. Now, these are just some of the reaction that you typically have. As you could see, you form a protonated base and a hydroxide. So that's the cue that you have a basic reaction, or you have a reaction of water with a base. So the way you solve problem here is just this, it's just the same as what we call the Ka. You will be given here the pH, the initial concentration, and the Kb. So from the pH, we can find first what? H3O plus and then hydroxide. So there's just additional calculation step because you don't get the hydroxide right away. What you get is just the H3O plus from the given pH. Okay? And using what is given, we can find what the other quantities. And just like the assumption that we have before, when the initial concentration is divided by the Kb is over 1,000, the expression is this: initial concentration minus X is just equals to the initial concentration. And I think I just only have one calculation here. So you have aniline. What's the pH of 0.035 molar solution of aniline at 25 degrees Celsius? So the Kb is equals to 4.2 times 10 to the negative 10. So what we're going to do here, C6H5NH, okay, react it with water. You produce C6H5NH2 plus. You don't have an N there. So it's not really a 2 plus, it's just NH plus and hydroxide. So that's water, just to make sure. So what is the initial concentration that we have? Anyone? What's the initial concentration that we have in the problem?
0.035.
So 0.035. We don't have anything at the beginning, and then you have what? What's the changes here?
Minus X. And then
Minus x plus x plus x. So you have here 0.035 minus x, and then you have here x, and you have here x. So you're given the Kb here. You're going to write this as C6H5NH plus times OH minus divided by C6H5N. Oh, there's an NH there. So that means that's an H2 plus there. So this is equals to 4.2 times 10 to the negative 10 equals to x times x over 0.035 minus x. Now, can we make an assumption that 0.035 minus x is just 0.035? So you get the initial concentration, which is 0.035, divided with the Kb, which is 4.2, exponent negative 10. So you get there around 8.3 times 10 to the 1, 2, 3, 4, 5, 6, 7. So we could say this is just equals to 0.035. So you multiply this with the given Kb, and then what? Get the square root, and that is your x. Now, what is your x? Your x is what? Hydroxide. So what do you get? Square root 4.2 exponent negative 10 times 0.035. Anyone? What did you get? Did you get this? Or around 3.8, not 3.80, 3.8 times 10 to the negative 6. But that's hydroxide. So the one that's being asked is what? pH. So how do we proceed there? I can convert this to what? A POH, which is negative log 3.8 times 10 to the negative 6. So what do you get? POH there. .42. And then from that, you can get the pH as subtracting that number with 14, so you end up with 8.58. Analyze. Question? Any question? Hello?
I don't have a question.
How are the others? You're still there? You're not sleeping anymore? I mean, you're still awake? So we get the pH of weak acid, we get the pH of weak base. What else we can get? Knowing a system at equilibrium. Okay? So the next thing that we can determine, aside from the weak acid and the weak base, is if we have what we call a salt solution. So a salt solution is usually made up of what? Cation and anion. And if we're going to look at this cation and anion, usually they came from acids and bases. Okay? Usually we could say that if we're going to look at the cation and anion separately, okay, it was a product of the dissociation of an acid or a base. And depending what is the source of this cation and anion, the resulting solution, okay, will be dictated by the source where it came from. So for instance, if you have NaCl, if you're going to look at the NaCl, if you break it down, what do you have? Na plus and Cl minus. And if you're going to look at this species, you could say that, oh, this sounds familiar. It can come from this. And this one, you could say, oh, it looks familiar. It can come from this source. So what is HCl? Is it an acid or a base? Anyone? Okay, so that's an acid. How about NaOH? It is an acid or a base? The NaOH.
I think it's a base.
Okay, so it's a base. So you could see the salt component just came out from an acid and a base. So in that case, you can predict what will be the acidity of the salt. Okay, so let's look at this one, Na plus. So it says here, the conjugate acid of a strong base is a very weak and does not react with water. Remember when we're talking about the relative strength, if you are strong in the reactant side, most likely the conjugate acid and the conjugate base that you form, okay, in the product side will be weak. So if you're going to react the conjugate acid of a strong base with water, there's really no reaction. The same thing, if you're going to react the conjugate base of a strong acid, so you have HCl on this side, when you have it with water, you're going to form H3O plus and Cl minus. So this is your acid and this is your conjugate base. And the conjugate base of a strong acid is very weak. And when you put it with water, there's no reaction. So what happened? Both of them came from strong acid and strong base. They will not hydrolyze, so you're going to have a salt that is neutral. Because the next thing that we're going to do is you're going to identify if a given salt is acidic, basic, neutral. Or another way to look at it, they came from a strong acid, They came from a strong base. Both of the acids and base came from strong acids and bases. So when you combine them, they will just neutralize one another. And the explanation that they have there is the reaction with water called hydrolysis. So if your conjugate acids and conjugate base came from strong acids and strong base, it will not react with water. There will be no hydrolysis. Only those that came from weak acids and weak base will hydrolyze. So let's have another what we call salt. How about if you have ammonium fluoride? So what can you say about the ammonium fluoride? So both of them are what? The conjugate acid of a weak base, okay? And the conjugate base of a weak acid. So both of them will undergo hydrolysis. So you only hydrolyze when you have a conjugate acid from a weak base or a conjugate base from a weak acid. What does hydrolysis means? Your ion react with water, and what it produces either an H3O plus or a hydroxide ion. And that predict what will be the acidity of your salt solution. Okay? Now, if you have ammonium fluoride as the salt, what could be the acidity and basicity here? Well, both of them produce an H3O plus and a hydroxide minus, so you still have to determine which one is bigger, the Ka or the Kb, which we're going to come back later on. Because as of now, this is the only information that we have. We cannot predict if it's acidic or basic because both ions will hydrolyze. So how do we know which one is stronger? We need to look at the Ka and the Kb value of those species that we're going to return as we go on other examples of salt solution. So this is an example of one that comes from weak acid and weak base. The previous one, strong acid, strong base, you're going to have a neutral solution. Weak acid, weak base, it depends. Okay? So if we ask to classify each salt here by examining its cation and its anion and then combining the results, so what would it be? So what would be the pH of your NaBr salt? So it's just A, B, or N. So what are the sources here? What's the source of HBr or Br? What's the source of Na plus? Because I already discussed that if you are a conjugate base or a conjugate acid of a strong acid or a strong base respectively, most likely you will not undergo hydrolysis with water. But if you are a conjugate acid of a weak base and a conjugate base of a weak acid, most likely you will undergo hydrolysis. So this one, both of them came from what? This came from a strong acid. This came from a strong base. So most likely they are neutral. How about this one? Where does the acetate came from? You have questions like this in the exam. So this one will come from what? Acetate would be weak acid, and this is what? Strong base. So that means if you have a weak acid here as a source, so you look at the reaction, C2H3O2 minus reacting with water will give you C2H3OH plus OH minus. So this will be, anyone? Base. Another way to know that this is a base because it came from a strong base compared to the weak acid. Remember the rule in the world? The strong ones dominate. So here, the source of it coming from a strong base will dictate you that the solution will be basic. How about the third one here? Okay, so again, okay, this is the one of the things. So it came from a base, so you could say it's a weak base, and this one came from a strong acid. So the one that came from a strong is the acid, so most likely it is acidic. Now, if you want to determine that it is really acidic, you're going to write this hydrolysis reaction. Which one hydrolyzes? The ammonium ion. So when you react it with water, what will happen? You form NH3 and H3O plus. So that itself says that it's going to be acidic. Now the last one, which we're going to what we call the, go back to what we have at the beginning. So we say both of them came from this one, weak base, and this one, weak acid. So the way that we're going to compare this one is, let's say NH4 plus and F minus. So both of them will undergo hydrolysis. So you react it with water, you're going to produce NH3 plus H3O plus. And this one, when you hydrolyze it with water, you produce HF and hydroxide. Now, what do you have there? Is it a Ka or a Kb? What K do you have in this reaction? Anyone? And what K do you have in the second reaction? Hello? You still there? So what is this K here? Is it a Ka or a Kb? Remember, I asked you this one earlier. How do you know if it's a Ka? How do you know if it's a Kb? So I'm asking it again at this time. Is this a Ka or a Kb based on the given reaction? So this one is, okay, since you produce an H3O plus there, that's a Ka. And this one, since you produce a hydroxide there, that's a Kb. That's the easiest way to remember them. Does that make sense? Now the question, is the Ka of this known? Or is the Kb of this known? Yes or no? If the Ka is the Ka of NH or NH4 plus given, or the Kb of F minus given, because usually what is given? the Kb of this and the Ka of that. Why? Why did I say the Kb of this is given and the Ka of this is given? Because this is what? A weak base and this is a weak acid. Now, if this is given, the Ka and the Kb, can I get the corresponding Ka of NH4 plus and the corresponding Kb of F minus? How do I get the Ka? Another thing that you will learn, Ka times Kb will give you Kw or Kw. So if I'm going to be that way, that means the Kb of this, the Ka of this one is just equals to Kw over the Kb of NH3. And this one, the Kb is just equals to Kw over the Ka of HF. Now that thing, I can get the information, okay? Because we have the table earlier. So to get the Ka here, so this is equals to 1 times 10 to the negative 14. And if you're going to look at the table, so this is what? Ammonia. So we have that information here. Ammonia is 1.8 times 10 to the negative 5. And then on the other side, you have Kb. So that's 1 times 10 to the negative 14 divided by the Ka of HF. And again, we have a table of the Ka here. I think it's at the very beginning. So HF, hydrofluoric acid, 6.8 times 10 to the negative 4. So I want you to get the corresponding Ka and Kb for them. Because that's the only way for you to determine what's the acidity of your ammonium fluoride. So 1 exponent negative 14 divided by 1.8 exponent negative 5. So I have here 5.6 times 10 to the 10. While the other one is 1 exponent negative 14 divided by 6.8 exponent negative 4. So I have here 1.5 times 10 to the negative 11. So what can you say about the Kb? No, this is not the Kb. The Ka and the Kb. Which one is higher? Which one is higher? Is it that one? Ka is higher than Kb. So what does it mean? Since Ka is higher than Kb, then this is acidic. So let's try to apply this concept in real life for those who want to be a doctor in the near future. So ammonium nitrate is administered as an intravenous solution to patients whose blood pH has deviated from the normal value of 7.4. Could this substance be used for acidosis or alkalosis? So I want you to use the reaction button that we have. So what do we have for acidosis? The thumbs up. And then the other one is for the clap. So where do you think you're going to use your ammonium nitrate? It is for acidosis or alkalosis? So I want to see your answer. Thumbs up for acidosis and then clap for alkalosis. So what do you think will be the acidity of your ammonium nitrate? Because that's the only way for you to determine where are you going to use that thing, in what conditions that you're going to use that thing. So remember, the idea that you have there is to maintain the pH blood of 7.40. Okay? I don't know if you're one of the people who believe that if you drink alkaline water, you're going to get a good health. Well, I'm sorry to disappoint you, but our system, as much as possible, has a way to maintain their pH as 7.40. So even if you drink a lot of this alkaline water, most likely your pH is still maintained at 7.40. Okay? And you will learn about that maybe today or next meeting. So what is this? Will it be acidic or basic? If you're going to dissolve it in water. Because that's the way you're going to be able to answer the question. So you look at the source. This is what? Strong acid. And this one, weak base. So you have an acidic solution. So to what condition are you going to add the acidic solution? So most likely a blood pH that is higher than 7.40, because what you're going to do when you add it to that higher pH, the pH will go back to 7.40. Does that make sense? Anyone? Are you still with me? Hello? Are you still with me? It's always the usual one, the usual people who answer the thing. So maybe what will I do when I do the grading and then I look at all these what we call chat messages. Okay, who's participating? That's why I don't erase all the messages that you have there until the semester is gone. Because when you reach this so-called am I going to push your grade up or you just remain as the present grade will tell you? So I always look at evidence. Is this student participating in the first place? So I always go back to this what we call chat messages that we have. Because I don't grade based on what we call gut feeling. I grade based on the input that you have. Because that's how I do it scientifically. Okay? So usually the thing is, as much as possible, if you are the quiet person like me when I was in college, at least when you are asked to participate, you participate. Oh, you won't believe that I'm a quiet person. To tell you frankly, half of my blockmates can't believe themselves that I end up as a professor because I'm very quiet during my college days. I only talk when I drink or when I get drunk. And they always say, when when you're drunk, you always talk about chemistry. That's why if I have people who are not in my same major, they don't understand what I'm talking about. Okay. So next thing that we're going to do here. So we'll talk about the hydrolysis. So as I told you, hydrolysis is just the reaction with water of the conjugate base of a weak acid or conjugate acid of a weak base. Okay. So if you have this hydrolysis equilibrium constant, you can use it in problems to determine the pH of a salt solution. So now we're going to deal with numbers before we just identifying if the salt solution is acidic, basic, or what we call neutral. But now there are numbers to back it up that it will be acidic, it will be basic, because the pH has a number, okay, to support the answer that you give, that if it's acidic, the pH is less than 7. If it's basic, the pH is more than 7. Okay? And we did this already indirectly when we try to get the salt of a weak acid and a weak base, where the salt came from a weak acid and a weak base. Okay? So we can determine the K for the reaction of the ion with water hydrolysis. So let's say we have ammonium ion reacting with water, it gives us ammonia and hydronium ion. So if you're going to look at that, that's the first K1. Okay, oh no, if you're going to look at that, that reaction is just the sum of these two reactions. What is the two reaction? The reverse of the base reaction and the one that has the KW. So if you're going to get the new K that you have here, okay, because this one is just what? Ka. Why? You have an H3O plus. This one is 1 over Kb because you have here the hydroxide. So if you're going to look at this as the reactant and this as the product, your K there is equals to Kb. But you reverse the reaction. So anytime you reverse the reaction, you get a new K that's the reciprocal of the previous reaction. So if you're going to combine these two reactions, this is what you get. So the 2H2 with the H2O was dissolved here, one of them. Okay, so we still have one. And then the OH is what we call cancel out. So what you end up here, you have an NH4, one H2O, one NH3, and H3O plus. So that's the Ka. And the new one is equals to Kw over Kb. So let's try to solve problem like this one. What is the Kb for the fluoride ion? The ion added to public water supply to protect it. I don't know, but during the 60s, this is the popular conspiracy theory that the Soviet are the one responsible for the addition of fluoride in the water supply. Okay, right now there's a lot of what we call conspiracy theories. Why? Because of the social media. Okay, the social media cannot censor stupid ideas that is being placed in what we call social media. So that's the problem right now. And the problem that we have in the society is usually the stupid people are just full of themselves. And the smart one are the one that is always in doubt. I don't know if you're going to believe with me in this saying, right? Because the evidence that I can give you is the president that won the 2016. You're more smart than that guy. Okay? So the conspiracy theory that they have during the 50s and the 60s is the fluoride is a product of communism. They put it in the water supply to at least control the mind of the people. So you're asking here, what's the Kb for the fluoride ion? Now we don't have the Kb for the fluoride ion, but we know it came from what? HF. So we can get the Ka. So all we need to do here, Kb is just equals to or if we want to what we call solve it in a way like a logical one, so you have an F minus reacting with water, producing, what do you produce? HF and hydroxide, which is equals to your Kb. And if you want it to be like the previous sum, like this one, so you can also use the problem that we have there. Okay, so we could say we have what? H2O reacting with F minus, producing HF and, no, not H2O, maybe H3O plus. HF reducing that one. So that is equals to what? If this is a K1, that is equals to 1 over Ka. I just reversed the thing here. And then we have water dissociating to give you H3O plus and OH minus. So that's K2, and that's just equals to Kw. And if we're going to add them, so we cancel, what can we cancel here? We cancel this. We cancel one of the H2O there. And you end up with F minus plus H2O producing HF plus OH minus. And that is your Kp, which is now equals to Kw over Ka. So if you're going to look at the Kb, so that's just 1 times 10 to the negative 14 over 6.8 times 10 to the negative 4. And this is equals to what?
1.5 times 10 to the power of negative 5.
1.5 times 10 to the negative 5. Everyone got that?
Yeah.
Yes.
Because I can also ask you, what's the pH? Oh, you cannot get the pH here because you're not given the concentration. You're just being asked what we call the Kb. I think the next question where we can get the is where we can get the pH, like this one. So bleach, which is 5% solution of the sodium hypochlorite NaClO, this corresponds to a molar concentration of 0.070 NaClO. So what is the hydroxide concentration and the pH of the given solution? So the way that you're going to do this will dissociate to give you what? Na plus and ClO minus. And both of them will give you 0.70 molar. And what will happen? Your ClO minus will react with water to give you what? What's the product that is produced? HClO and hydroxide. So right away, you could say that it is what? A basic solution, because this comes from a strong base. This comes from a weak acid. So the one that's being asked, what is the hydroxide concentration and the pH of the solution? So you can do it like this. And what do you have? That's reaction, initial, changes, equilibrium. So you have initially 0.70 molar. You don't have anything here, and then you have minus X, and this is what? 0.70 minus X, and then you have X, and then you have what we call X. So you will end up with Ka or Kb equals to HClO times OH minus divided by ClO minus. What is that? Ka or Kb? Anyone? So this would be a Ka or a Kb. So this is a Kb. What's my guide? I have a hydroxide there, but the Ka, the Kb is not given. What's given is the Ka, so I can make this as Kw over Ka, and then I put there X times X over 0.70 minus X, and I think initial concentration 0.70 divided by the corresponding Kb here. So what will be the Kb here? 1 times 10 to the negative 14 divided by 3.5 times 10 to the negative 8. That is equals to what? I have here 2.9 times 10 to the negative 7. So that will be x squared. And I think this is just equals to 0.70. Because 0.70 divided by 2.9 exponent 7 will give you more than 1,000. Okay? So you solve for x here, which is just 2.9 times 10 to the 7 times 0.7 and get the square root. What do you get? I get this value, 4.5 times 10 to the negative 4. But that's just the x. And that is equals to your hydroxide. So it answered the question here. Now for the pH, what do? Maybe you can get the log of negative log of 4.5 times 10 to the negative 4 to get the pOH, and then you take the pH. So if I have a negative log, so what is the pOH that you get? Do you get a 3.5?
3.5. I mean, oh yeah.
And then to get the pH, that's around 10.65. Now you may ask me, Professor, what's the guide if my answer is correct? So if the pH is more than what we call 7, you have a basic solution. If it's less than 7, you have an acidic solution. So question, I think we will end at this juncture because it's already 1:35. So I'm going to send you the link if you want like extra credit for a seminar tomorrow. The way that it's going to do with it is you have to write something about the seminar. Attending it, it's not enough. Okay. And then the chapter 15 quiz is already available and it will be available until 12 p.m. next meeting. And if I'm not mistaken, the OWL is deadlines today. I think 14 and then 15 next meeting. The seminar tomorrow, I think is at 12 o'clock. Okay. So question, Monica.
Yeah, I was gonna ask when you for lab when you were gonna like post the lab 18 like how to do it, like the PowerPoint that you usually do.
I only do it if I see that there's need of a calculation. If you don't have a calculation, then usually you will learn it on Thursday because I look at my Wednesday class for every corrections that need to be corrected.
Okay.
Because I cannot do the correction right away on a Monday. I have to look at further mistakes on the Wednesday lab section that I have. So my advice to the Monday class that they have, don't submit your lab report until you see a correction from it. Okay. So the earliest is after I have the lab on a Wednesday, the latest would be like a Thursday. And I think some of the Wednesday class email me that they don't know how to do the calculation. That's why I have to do a PowerPoint slide on how to do the calculation on experiment 17. So the thing that you do it is, if you need help, you email me. Don't assume that you're not going to be denied. Okay? The Bible say knock and it will be open. And I'm saying it open and it will be knocked. So if you have like what we call the hard time with the course, you email me. And when you email me and when I email back, you have to be specific when I ask you something. Because if you're going to return to me, it's up to you. And if I'm giving you that option and you're giving me that option, well, if I give that final answer there, then you don't have any choice but to follow that option that we're given to you. Okay. Some of you understand what it means because you emailed to me and ask for specific help. Some were given, some were not. But just email me, okay, so I will know. Okay. I think it should be, the owl should be due at 5, if I'm not mistaken.
Yeah, it's due
Okay.
at 5 too.
Professor Mojica,
Yep.
the chapter 15 quiz shows that it's due tomorrow at 12.
Okay, I'm going to what we call that. Look at it.
Okay, thank you.
So any more before I close the thing? Because I have to fetch my Unica Iha.
Professor,
Yes.
I was wondering if we could push back the chapter 14 owl at least till midnight today, if that's okay.
Now we will see. That's why I told you, you email me. Okay.
Yeah, I was gonna email you anyways, but yeah, since you're here.
Okay. Now, so it's already 1:38. I have to go. Okay. So if you need anything, email me.
Okay.